For 200 years, we've been designing machines wrong. Not slightly wrong, fundamentally wrong. That bracket wasn't drafted by an engineer. It wasn't sculpted by a designer. It was grown by an algorithm, optimizing for forces humans couldn't even visualize. And here is the thing nobody asks. Why does our most advanced technology suddenly look like it was grown in a forest instead of built in a factory? This isn't an aesthetic trend. It's not a design movement. It is a signal that something underneath engineering itself has permanently changed. For 2 centuries, engineering spoke one visual language: beams, grids, right angles, symmetry. Look at a Model T chassis, a steel bridge, an aircraft rib from World War II. They share the same geometry, and we assumed that geometry was optimal. It wasn't. It was manufacturable. Industrial tools shaped what engineers could imagine. Lathes made cylinders. Mills made flat planes. Presses made uniform sheets. So we designed around those constraints, not around physics, around tools. And hidden inside nearly every machine built in the 20th century was something engineers quietly accepted: the weight penalty. Material that exists not because it carries load, but because removing it was impossible, impractical, or too expensive. Dead weight. Engineered in. In commercial aviation alone, engineers estimated that traditional manufacturing left 20 to 40% of structural material carrying almost no load. Dead weight, on every flight, for decades. Across entire fleets. Across entire histories of fuel burn. How much of modern engineering is just compromise we stopped questioning? If this kind of thinking interests you, the systems, the incentives, the real logic behind how things work, hit subscribe so you don't miss our next deep dive. In 1892, a German surgeon named Julius Wolff documented something that took engineering a century to catch up to. Bone isn't static, it adapts. Apply load repeatedly to one region. Bone deposits material exactly there. Remove that load. The bone resorbs what it no longer needs. Dense where force flows. Porous where it doesn't. Bone is a physical map of stress. Nothing more, nothing less. Both structures are solving the exact same equation. How do you carry maximum force using absolute minimum material? Nature has been running that optimization for 400 million years. Human engineering guessed. Added safety margins. Then added margins to those margins. We overbuilt because we couldn't calculate precisely. But by the 1980s, we could. Topology optimization existed. Finite element analysis existed. The math to design like nature. We had it. So why didn't everything change then? Because knowing the optimal shape and building the optimal shape are completely different problems. Traditional manufacturing is subtractive. You start with a solid block. You cut away material until a shape emerges. Now imagine trying to carve the inside of a bone. Internal lattices. Organic curves. Hollow voids suspended within solid walls. Impossible. The shapes that were theoretically optimal for 50 years were physically unreachable. The math existed. The ability to build the math did not. Then additive manufacturing arrived. Not plastic trinkets, industrial metal printing, titanium, Inconel, stainless steel. Built up from powder, layer by layer, exactly where physics says material should exist. Nowhere else. For the first time in history, we could manufacture the shape that physics actually wanted. 2 tools emerged. Same philosophy, radically different methods. Topology optimization is a sculptor. You begin with the maximum possible material envelope. Then software removes what doesn't carry load, iteration by iteration, until only load-justified structure remains. Generative design is evolution. You don't draw anything. You define constraints, load points, weight targets, material properties, manufacturing method. Then the algorithm breeds solutions, thousands of them. None symmetrical, none intuitive, none human-looking. Because they aren't optimized for human visual intuition. They are optimized for stress paths, for force vectors, for physics. And physics, it turns out, does not care about right angles. Bone looks alien too. until you understand what it's doing. Airbus redesigned one cabin bracket using generative design. 45% lighter. Same structural performance. One bracket. Trivial. Now multiply that bracket across an entire aircraft. Multiply across a fleet of 800 planes. Multiply across 20 years of fuel burn. One redesigned bracket, applied fleet-wide, is worth hundreds of millions of dollars in fuel savings. That is not aesthetics. That is economic leverage at civilizational scale. Medical implants now mimic bone porosity so precisely that real bone grows into the metal lattice. The implant doesn't get rejected. It gets integrated. The machine becomes biology. In performance cycling, frames are no longer designed. They're grown from rider force vectors and vibration frequencies. No guesswork, no overbuilding, just load-justified structure end to end. But here's what nobody talks about. This logic doesn't stay in aerospace. Step back. This is not a story about bike frames or aerospace brackets. It's a story about who, or what, is doing the designing. For 200 years, humans drew machines. We imposed our geometry, our intuition, our manufacturing constraints onto matter. Now we set constraints and let algorithms evolve structure. We are not drafting anymore. We are curating evolution. This shift moves into architecture, infrastructure, drug molecule design, energy systems. Wherever optimization matters, and it matters everywhere, this logic propagates. The companies and nations that master algorithmic design first don't just build lighter products. They operate at a different layer of physical reality. And in a world constrained by energy, materials, and capital, that difference is power. We didn't start building like nature because we admired it. We started because inefficiency became too expensive. The straight line wasn't optimal, it was convenient. Now convenience no longer defines engineering. Physics does. And the future of engineering isn't mechanical, it's biological.